Okay. So a couple announcements, and then today what we're going to do is we're going to review more Monte Carlo approximations because I want to make sure that everybody kind of gets a handle on Monte Carlo. Okay. We'll also continue with the homework and go up through part 3 of the homework now. Okay. So first off, right, you want to have your pre-proposal turned in. Ideally, on Thursday, what you would like is to have your proposal finished before you come and see me, and then just make a few modifications as need be. So wait, Thursday is going to work. Remember, Thursday... Sorry, 1 second. Wow. Okay. 1 second. All right. Remember, for your final project, the way Thursday works is that... first off, I will be holding... I've decided that just to make it easy, I'm going to do Thursday over Zoom. That way, so nobody really has to come in on Thursday. I will be holding it over Zoom. I'll boot up Zoom, and basically I'll just try to meet with you all with regards to your project. Every group has to meet with me, but everybody does not have to meet with me, if that makes sense. So in other words, if you're part of a group, you can meet together. All 3 members of the group don't have to meet individually one at a time. So I would recommend all members of the group be there and meet me together, but I don't have to meet for the same project 3 times in a row. Make sense? So if you don't have a proposal or an idea of what to do, I will basically help you figure that out very quickly on the spot. Remember, you have to meet with me and get approval for your idea before you can, in order to actually do your final, in order for you to get checked off to do your final project. Make sense? Okay. The exam will be, next Thursday on the 16th. Okay? So we're going to do that on the 16th. Tuesday will be a review day. Then when we get back from, I think then the next week after that's the Thanksgiving break, right? Then after we get back from that, we will do the regular expressions and a few more other things to kind of get us toward the end of the semester. Okay, so again, come prepared with the proposal next class on Thursday. If you aren't able to meet with me on Thursday, then it's your responsibility to meet with me as soon as possible after that. Okay. So what I'm going to do is go over Monte Carlo, which is again the part that I think most of you are that feels the new most difficult to a lot of you at the moment. So we're going to go over various things. First thing I'm going to go over is I choose this example because it's different than what we've had to deal with before. If you haven't checked out, if you haven't gotten to know me or checked out my About Me page, you may know that I've got a lot of interests. And one of those interests are role-playing games like Dungeons and Dragons. These days, I'm playing Dungeon World. I've also been a fan of them, and I've really fallen in love with the game system Monster of the Week. I find I like more abstract game systems these days, and one of those systems I enjoy is something called Fate. Now, Fate is a very interesting system. The way that a lot of things that are dealt with that involve random chance in role-playing games is that you make a roll of some kind. You roll some dice. Okay? And but what kind of dice and how you roll them depends on, that really changes the outcome of what's going to happen. For instance, if you're rolling a single-sided dice, all outcomes are equally likely, right? If I have a 6-sided die, 1 through 6 are all equally likely, meaning that chances of absolute success and absolute failure are equally likely. Your highest results and lowest results. Some systems like Fate or Dungeon World, they use multiple dice, which means that your outcome is more on a bell curve, meaning that your most extreme successes and extreme failures are very unlikely and very likely, and are very unlikely in both regards, and your average around, and you have some average result. So fate is fairly straightforward. The way the dice work in fate is that you roll something called a fate dice. Roll, and I'm going to call that def roll df. Okay. And what a fate dice is that it is a six-sided die with the following faces on it. And this is why I wanted to bring this up as an example. And then we'll give a problem. Okay? So a fate die has 6 faces. 2 of the faces are marked with a plus symbol. 2 of them are marked blank, and 2 of them are marked with minuses. So plus, nothing, and minus. Make sense? You got 6 sides. 2 of them have pluses. 2 of them have minuses. 2 of them are blank. So when you play that game, what you do is you roll 4 of these dice and you add up the result. Pluses are 1s. If for pluses you add 1, for minuses you subtract 1. Right? And it doesn't take, and you can instinctively kind of know enough about statistics, just out of instinct from being a human being, that if you roll these 4 dice, on average, your most likely result is going to be a 0, right? You've got 2 that have, if you roll 4 dice, you've got 2 sides that are going to give nothing, and then your pluses and your minuses are equally likely. It's possible you could roll 4 pluses, right? Or 4 minuses, because you've got 4 dice when you roll these things. You roll 4 of them at once. So I'll go ahead and put that down as roll 4df. Okay? But those kind of, but that is not necessary, but those are more extreme. So the range of outcomes, as a result, range are in this range. They are in the range of -4 to +4. And I want to know, and when I typically ask this question, I ask something like, what are the chances of getting a 3 or better on a roll? That's what I want to know. What are the chances of getting a 3 or better? Okay? So, first thing we want to do is simulate rolling this dice. And that's why I bring up this problem, because it's not got numbers on it. Now, we could just simply, we could have these numbers, right? We could make these numbers, right? I could make a dice that I could do -1, 0, 1, and just kind of draw one from an integer range. But what if I didn't want numbers or something? What if I was dealing with a different kind of dice that couldn't be added, couldn't add up my results? So what I want to show you is a very useful function in random called import random, and it's something called random.choice. So let's go ahead and first mark down our faces for the dice. So this is the various results that our die could have. They could have a plus, comma, a plus, comma, they could have a underscore, another underscore, and then a minus, and a minus. And I'm doing it this way because I want to, because rather than taking a shortcut, I'm simulating it as strictly as I can. Okay? So here we go. Those are the faces of the die. I think what I'll do is I'll have a roll 1 df, roll for rolling a single die, and then I'll use that to write the 4-sided die. So roll 1 df. Okay, and I completely copy, Control Z. There we go. I copied when I had nothing. There we go. So faces, there's our faces. And so what we would do to basically select one of these 6 options, okay, is that I would be able to say result is equal to random.choice faces. And I love random.choice I believe it should exist in all programming languages. What it does is that it selects one of these options at random. Okay? And we can return, and we can just return the result, I think. Yeah, we probably don't need a roll for df for this. Def sim, yeah, sim4df. And so this will simulate. So this one will simulate our what the result of rolling 4 of these dice are. So what we'll do is we'll say 4 in range 4. So for a roll, so a fate roll has 4 of these dice. A roll in the game of fate has 4 of these dice. We've figured out how to roll a single one of these. Now we say, okay, I want to get a numerical result that occurs from rolling 4 of these things. Okay, so how do I do that? Well, I will call roll 1df, and that gets me the result. And then I got to translate this result. Now there's 2 ways to do that. I could do an if-else statement like this. If result equals is equal to the plus sign, go ahead and say total. We do a running sum here, and we say total is equal to 0, total plus equals 1, if result equals minus total minus equals 1, right? And then if it's left blank, I'm just adding 0, so I won't change anything, right? So plus, add 1, minus, subtract 1. Otherwise, don't do anything. The other way you could do it is you could set up a dictionary, but that's not really necessary here. And so we roll 4 of these dice, return the total. Right? What you don't want to do is call this function and try to multiply the result by 4. That doesn't give you what you want. Okay? So we roll 4 individual dice, we check it, and we convert the result from pluses and minuses to a actual result. And then we do our simulation. Trials is equal to 1,000. Let's do 1,000 of these. Higher, and we can do a couple of things. Higher than 3 is equal to 0. 4 in range trials. 1 roll. Not roll, but sim. I called it sim4df. It's equal to sim4df is equal to, let's say result is equal to that. Or I'll say roll is equal to that. And then if roll greater than or equal to 3, higher than 3 plus equals 1. Turn, and then print, and then we're done. Print out higher than 3 divided by the number of trials. Okay, and hopefully I didn't miss up somewhere. And so it says I've got about a 6 to 7% chance. It says 0.67, so that's about a 6 to 7% chance of rolling a 3 or better, right? It says 8% over there. So if I do, if I do 100,000 of these rolls, I get a much more constant result, which says about 6%. If we wanted to do something else and check higher than 0 instead, we could also check out that and keep track of that as well. If roll is greater than 3, higher. If roll greater than or equal to 0. This is a really inefficient way to do it, but whatever. Higher than 0 plus equals 1, and then we could just simply do the same thing. So we could see, or rather, it's not higher than 3. Let's call it's 3 or better. 3 or better. And of course, that means I have to change this 0 or better, right? If you're writing your code and you realize your variables don't match, you should fix that. And so we find that basically you have a better than, you have a 6% chance of getting a 3 or a better, which is pretty good. Sorry, that's uncommon, but it makes it fairly exciting when it does happen. And then you've got a 60% chance of not rolling a 0 or better, of getting the average result or better in this system, which leads to some, satisfying results as a player. Okay, so let's go ahead and take a look at one from, now we're going to take a look at some from the practice exam and some former quizzes that I've given, now that we've kind of given that as a nice warm-up. Okay, so let's go ahead and go to, let's see, ITP, teaching. And I'll put up a practice exam when I compile all of it into a practice exam in a bit. So exam to practice. Let's see, does this have the Monte Carlo's problems that I'm looking for on it? So these will be on part of the practice exam, but I feel like some of these are worth going over now. Nope, this is practice 2, so this is on practice 3. Here we go. All right, first up, let's see. No, that's a completely different. Oh, I've got multiple final exam, Monte Carlo problems to give to you. And now it's crashing on me. That's very interesting. Why is that happening? How fascinating. Okay, open in Firefox then. And this was for the practice final that I put together. Let's see. Oh yeah, there it is. This one's one I stole from last semester. So ignore the disclaimer on top. I have to make a brand new exam because of the way, or brand new practice exam and exam because of the way that stuff is structured. I should have that out Thursday evening. So this one was pretty good. So let's talk about coins. Coins are, so for the problem that I give you on your exam, you can expect it to involve either rolling basic dice or rolling or flipping coins. Okay, keeping things very simple and easy to and familiar and grounded. Okay, so this one's a fairly but they'll typically be of this form, which is that I'm presenting you with something that seems fair and is very not fair. Okay. So the outcome of any fair coin toss has an equal chance of landing on heads or tails, correct? You flip a coin, it lands on either heads or tails, 50% chance, right? So if I toss a coin 3 times in a row, there's 8 possible outcomes, 2 to the 3rd power, 8 possible outcomes, right? I could get 3 heads in a row. I could go head, head, tail. I could go head, tail, head, tail, tail. And then, so those are all the sequences that start with head, and then I have 4 sequences that start with tail. Tail, head, head, one where the tail, head, tail, 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 head, and then tail, tail, tail. 3 tails in a row, 3 heads in a row. Then I've got 2 of the first one in a row, and then it's flipped. Then where the middle is different, and then where the first is 1, but the latter 2 are different. Okay? And H and T here represent heads and tails. So you've got H and TT is 2 heads in a row followed by a tail. So suppose I challenge you to a coin flipping game for $100. Pretty big stakes for college students. Okay? So you will choose a sequence that occurs after 3 coin flips. Okay? You'll choose one of these sequences that occur after coin flip. I want you to be able to choose first. After all, that way you've got your pick of the pick. You know, that way it's not rigged or anything. You can choose which one. It doesn't matter. And then I'll pick one, okay? Okay, so suppose you pick something like head, head, tails, and then I'll pick a sequence like tail, head, head, okay? So one of us, doesn't matter which one of us, will keep flipping a coin until one of our chosen sequences will appear. So, for example, if you've chosen head, head, tail, and I've chosen tail, head, head, this is how some outcomes, somehow sample games might work, right? Head, tail, head, tail, head, tail, head, head. Tail, head, head is my sequence appeared first, so I won that game. Tail, head, head. You flip head, head, tail, you win that game. I flip, and then if we simply flip tail, tail, head, neither of us chose that, so then we flip another tail, nobody wins because tail, head, tails is not a chosen sequence. Then head, tails, heads, then tail, head, head. That's my sequence up, right? Once we get right, we'll keep throwing this until the last three is one of our chosen sequence. In that case, I would win, and then you flip a bunch of heads in a row, and you flip a final tail. That's your win. Make sense? We keep flipping until one of us wins. All right. So this seems like a fair bet. After all 8 outcomes of flipping a coin are 3 times are equally likely. Then you remember that Professor Rosen once mentioned he would be sorted into Slytherin and is a bit of a trickster. So he probably wouldn't be challenging you unless he was going to win. Seems like a fair game, though, right? But of course, if I'm asking you this, if I'm presenting this as a question in class, this is anything but a fair game. This is in fact a huge scam. Okay, so let's write a program to simulate the game and see if the professor is trying to scam you. And once we do, and I'll have that link there to show you the full idea of the game. But this is a game called Penny's Game, Penney. It is a fairly common scam or bar scam. So So what we're going to do is that we're going to simulate this game on the previous page with one player trying to get head, head, tail, and the other trying to get tail, head, head. Have your program simulate the game 100,000 times and print out the percentage of times 2 players win. And let's go ahead. Did I include a rubric here? No, for this problem I did not. I did not include a rubric here. For most of these I will be including rubrics, so no worries. Let's go ahead and simulate this game. Okay, so first things first, let's go ahead, before we get into the game, let's just go ahead and simulate flipping a coin. Flipping a coin can be done in a number of ways. Because we're tracking heads and tails, let's go ahead and just literally write down the strings heads and tails. But you could do it by rolling a random number between 0 and 1, right? Just simply getting a literal random double. Or you could go and get a random number 1 or 2 or 0 and 1. I'm just going to keep it simple. I like to make my things as simple as possible. Flip, I'm going to say sides are equal to, and you could do this as a string, but I'm going to do it as a list, head, and tail. Those are the 2 sides of a coin, right? And if somebody has a 3-dimensional coin or something like a 3-sided coin, this would work as well. But that's not, because again, what we're going to do is we're just going to return random dot choice. If we didn't have random dot choice, then we'd basically effectively have to write it. And the way that would work is we'd probably have to say something like, if we didn't have it, don't write this down, we'd have to do something like index is equal to, random dot rand range 1 and 2. Oh, sorry, 0 and 1 rather, right? And just randomly choose an index from there. But this kind of sidesteps that whole idea and just gives us the result, either heads or tails. Def, play, Penny. And that's the way I believe that's spelled, E-Y. So let's go ahead and play this game. We're going to have and we're going to take in, again, for here it says right, with one player trying to get head, head, tails, and the other trying to get tails, heads, heads, I'll abstract that out and make it just sequence 1 and sequence 2. Make sense? And then we got to figure out what we want to return here. Okay, we could either do true or false to do this. So like true if player 1 wins, false if player 2 wins. But that might be hard to keep track of. I'm going to just switch it up this time around. I'm going to return 1 if sequence 1 wins, and 2 if sequence 2 wins. Make sense? You can do whatever you want. Just make sure it kind of makes a sense. Here we've got sequence 1 and sequence 2. Returning 1 or 2 makes sense. Okay. So what we want to do is we want to generate, we want to do our, I'm going to call this coin flips, plural, and make it a bigger name so that we don't confuse it with the flip function. Just, okay, and it's just a string. Now we don't know how long this is going to go on for, so we're going to use a while loop, right? We use a while loop. While, and honestly, this is going to go on for, the way I think I should do this is that we only want to stop when we've identified a sequence, right? So we could do something like while not done, right? While not done, and have a done set to false, right? And while it's not done, keep doing this. But honestly, we could just do something that's generally ill-advised, which is a while true. In other words, do this forever until we break the loop. You can either break the loop with the break statement or a return statement, because we want to stop as soon as we've identified a situation. And once we've identified it, we want to return. Sorry, once we've identified a winner, we want to stop. And when we stop, we'd want to return anyway. So might as well just do that all in one step by returning. So while true, coin flips, we need to flip another coin. Coin flips, and the way to flip another coin and add it to our long sequence of coins that has already been flipped is just concatenation. Coin flips is equal to coin flips plus flip another coin. Or you could just write plus equals flip. And that will add a H or a T onto the end of it. Okay? Now, if you want to be paranoid about this, we could just simply do, we could flip in advance, a few coins, but there's no need with Python, because what we're going to be using is slicing. And remember, slicing works no matter what. Or at least I'm going to double check it works no matter what here. Just 1 second, because we've been slicing, right? Going out of bounds and slicing doesn't seem to matter, but I want to check just something. Here's an empty string, which is how we would start it. Or rather, it might be something like this. T from -3 to the end. Yeah, works. And what we want to do is get the last 3 characters of this, right? We want to get the last 3 flips, right? What we care about is that we stop once somebody has won, once somebody's sequence has been flipped. And if the sequence has been flipped, it always occurs in the last 3 characters, right? We stop when here because we've got tails, heads, heads. Here we've got head, head, tail. Here we've got tail, head, head. Here we have head, head, tail. It always stops in the last 3 on, right? Okay. So, and we don't want to just do 3. Now one of your thoughts might be, why don't I just do 3 coin flips and then discard it and just do another 3 coin flips? And that's because that's actually a completely different game. We're not. That's the lie there. If we were doing 3 coin flips and nobody won and just discarded it, and then did 3 coin flips again, then all options have a 12.5% chance of occurring. Here, though, what we're asking for is flip a coin until one of the sequences appears in the last 3 characters. And that is a completely different question. That's where the scam is. It's a completely different statistical question. So as we'll see, flip a coin, okay, and then we ask if coin flips from last 3 characters to the, so here remember -1 would mean from the last character to the end, from -2 it would be from the second to last character at the end. Here we're saying the last 3 characters to the end. That's the slice. Gotta love the negative slices in Python. They're amazing, right? From if coin flips -3 to the end is equal to our first sequence, I'm just going to return 1 for player 1. If coin flips -3 to the end is equal to sequence 2, return 2. And that's it. That's all we need. We don't need anything outside the for loop. The while loop. This will just keep going on forever and ever and ever until somebody gets that sequence. Make sense? So let's go ahead and just test this before we do this, because always want to test something when you've done a very dangerous, ill-advised loop like this one. And ours were head, head, tail, and tail, head, head. And then we want to print out what the winning, and then we will print out the winning sequence. 2 was the winning sequence, 1 was the winning sequence, 2, 1, 1, 2, 2, 2. Not enough really to make a result, although now we're starting to get an idea when we see 2 appear a bunch of times. So now what we need to do is we need to simulate this. So let's go ahead and take this part over here that we had with our original trial for the fate rolling. Move that up here. Okay. Flip coins. Coin flips. While true, flip the coin. Play the game. Okay. And so, let's see. And it was head, head, tail, and tail, head, head. Okay. And now what we're going to do is we're going to say trials is equal to, I think I said I want it to be played 100,000 times. We're going to play 100,000 of these games. And let's see. Player 1 wins. It's equal to 0. Again, you can call it wins or whatever. I'm just being very expressive today with my variable names because it doesn't cost me anything to write down extra characters. Okay? For blank in trials. Not trials, but in range trials. For blank in range trials. I make that mistake all the time. And I make it enough that I instantly correct it after making it, before I even run it. So don't feel bad if you make that mistake. I make it all the time. Just, the point is you got to make these mistakes enough times to be able to correct it. Okay? For blank in trials, play penny. So here we can take this out. If play penny is equal to 1, player 1 wins plus equals 1. We don't really need to do anything else. We don't need to have a case for 2. We certainly don't want to play the game again. I'm just playing the game in the if statement because it's either we win or we don't. We don't need to keep track of anything more than that. Okay. Okay. And what we'll do is that we will print player 1 wins divided by trials. And you'll see, actually, the win rate is, let's see. Oh, that's divide. We don't want to do that. Of course, it's going to be 0 because it's a smaller number divided by a bigger number. Yes? Yes, I do. Plus equals. I just probably didn't mean to, I probably meant to hit it and just didn't. Okay, there we go. And now we see that the sequence that, in the example sequence, if you choose head, head, tail, and I choose tail, head, head, I'll win. I'll win 75% of the time, and you win 25% of the time. So it is a total scam. But why? Why? It's because again, I kind of the lure was I was gonna let you choose first, and what happens is because I let you choose first, that means I get to subsume your sequence. Let's take a look at the examples again. If you choose tail, head, head, what's common between your winning sequence and your winning sequences? You've got head, head, tail, and head, 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 tail. That's your winning sequences. When you roll a bunch of heads in a row and then flip a tail, that's your winning sequence. My winning sequence is a lot more varied. Basically, as long as we throw a tail at some point, as long as we throw a tail before we get 2 heads in a row, at some point, that's great for me. Here, head, tail, and once we throw a tail, that's the beginning of my sequence. A tail is always the beginning of my sequence. So tail, head, head is always going to appear before head, head, tail. Doesn't necessarily make sense. Again, what I have to do is I need to choose a sequence that will basically subsume yours. Make sure that yours only appears in a very limited situation. Right? Over here, again, when we have tail, tail, once I've thrown like tail, tail, if tail, tail gets thrown, again, the only way you can win, there's no way to win for you, because as soon as we roll 2 heads, I win. This is called Penny's game. We look it up on Wikipedia. It's actually got a fairly straightforward strategy, which is that if your choice is, if player 1 chooses 1, 2, 3, right? You make your first choice, your second choice, and your third choice, whatever those are. Then all I have to do to win is choose not the reverse of your second choice, and then the first 2 of your choice. So, right, with head, head, tail, I flipped your second choice, and then did your first 2 choices. So that's why I chose tail, head, head. And that ends up being, and that's, it gets even worse if you end up choosing 3 heads in a row. 3 heads in a row, head, head, head. So I flip your second choice and then choose the first 2. So it's the same choice for me. So the win in that rate is 0.12. Your chance of winning is 1 in 8, which is the chance of getting 3 head flips in a row right out of the start. This is not a nice game to play, but it's actually a fairly interesting mathematical kind of phenomena. Because again, you wouldn't think it. But because of the way the problem is presented, it's not your initial thoughts in mathematics. So it's a lot. I find that one to be a lot of fun. Okay. Let's move on back to the homework before moving on to more problems. Okay. So going back to Pig. Let's see. Let's see. 1 second. Projector mute. Open recent, and that should have Pig in there. Or did I do Pig in? Or did I do that in idle? 1 second. Recent files. Or did I do that over Zoom? I don't think I did Pig over Zoom, did I? No? Yes, I did? Okay. Did I share it on Discord? Did I drop it on the Discord or no? Okay. Give me a second. I've got to make a pull from GitHub then. Sorry, it's on my other computer, the code then. 1 second. Classroom. Or have I not? Interesting. could have sworn I stored it on, I shared it. All right. Oh, here it is. Pig. All right. So let me go ahead and, all right. Yeah, that's got more of the hold X outcomes. Yeah, that's, all right. So let's go ahead. So I'm going to go ahead and grab last semester's work just so I can show you. It's going to give you a different perspective on it. Okay, Pig F 2023. Okay. There we go. And then what we'll do over here is that hold at 20 and change this back to 20 for a second before I go and change that. All right, and this is where approximately where we had. So again, the game of Pig, that's a game of, it's poorly named because it's technically more of a game of chicken, right? To see, can you keep rolling a die until you roll one, okay? So we were simulating a strategy for the computer. The strategy for the computer was roll, let's go ahead and roll a six-sided dice, okay? Which is just simply rolling choosing a random integer between 1 and 6. And we roll that dice. And let's go ahead. And for part 1, what we did is we did this. We said, hey, I have less than 20 points, I'm going to roll the six-sided dice, print it out. If my roll was a 1, I lose all my points for the turn, return that amount. Otherwise, I add on to that amount. And then I stop once I'm at 20 points. So if we do that, hold at 20. Right? Here we rolled a 1 at the beginning. Here we rolled a 2, 2, 4, 5, 3, 4. So we got 20 that turn. Okay? The next one is was hold at 20 outcomes, which I'll go over how I did that one for last semester in a second. I did it one time last semester and one time this semester. So let's see how I did it last semester. Well, the 20 trials. It says, how many times did we want to do this? Let's do it 1,000 times. Oh, common thing that happens a lot of the time. Let's go ahead and terminate this. Remember, if we're reusing these functions, you might want to turn off those print statements, because otherwise it will take forever. And this gives us, and the entire point of this exercise is that this gives us the statistics for our rolls. A 60% chance of getting 0, a 20% chance of getting 20, 21% chance, 10% chance of getting 20, 21% chance of getting, 10% chance of getting 21 points in a turn, a 7% chance of getting 22 points in a turn, 5% of 23, 3% of 24, and about a 2% chance of getting 25 points in a turn. Okay, those are our outcomes. How does this work? Well, what we do is that I hold a 20 outcomes, and I say, hey, I have a certain number of trials, okay? I want to do 100,000 trials, right? This question is like, I want to find out the statistics, how well this strategy of holding at 20 works. Here I'm saying, let's keep track of the outcomes in the dictionary. Now, 0 is always going to be an outcome, so I'm going to store 0. And just simply for future-proofing this, what I've done is that I've left it blank. And then actually last semester I did something I should have thought of last class, which is that I know that the range of possible outcomes are going to be 20 to 26, so I just simply populated the outcomes with those so that it would be in order and I wouldn't have to sort it. Okay? Make sense to everybody? So I said, okay, my outcomes are 0, and then they're also 21, 22, 23, 24, and 25. So what I did is I said, hey, do a hold at 20 simulation, get how many points that was, and then print, and then add 1 to the number of respective outcomes. So if I ended up with 0 points, I added 1 to the number of 0-point outcomes I got. If I got 20 points, I added 1 to the number of 20 points. If I had 70, if I got 24 points, I'd add 1 to that. And then once I'm done, for every one of those scores, I'd print that out. We're going to do the next part from scratch rather than copying and pasting it, just so that we can walk through this process again. And then I just print out the scores, and then the number of times I had that score divided by the total number of trials to get the percentage. Okay. Part 3 asks us a separate question, which is, okay, your strategy is hold at 20. What if it's more hold at whatever we want it to be hold at? Like, it's the part 3 is called hold at X. And what it asks is, given the number of trials you have, a limit and the number of trials, or rather, let's do trials because limit in trials. So what am I asking here? Well, we've been testing hold at 20, but suppose I want to know what if my strategy is hold at 15 or hold at 10. I want to see what my chances are if I do that are instead. Okay? So now I could rewrite this first function, but that would be a bit of a pain. Like copy it and rewrite it. Instead, what I'm going to do is I'm going to make use of something called default arguments, which is I'm going to add back in what I removed when I opened this file up. Limit is equal to 20. And I've shown this in class once, but it's worth showing again because it's a useful tool, even though it's totally not necessary. You don't need it. So I have hold at 20, and I say limit is 20, and then I say limit over here. That's all the changes I need to make. And what this does says, if you don't provide me an argument, this declares an argument called limit. And notice that now it's while the turn total is less than limit now. Okay? And what I'm saying is limit is equal to 20. If you give me a limit, if you provide me an argument, great. Then the limit will be that amount. If you don't, no problem either. It's going to be 20 by default. So limit has a default value of 20. This is how we've seen this before with opening a file and printing an argument. Print actually takes in a bunch of arguments. It has a bunch of arguments. Roll. So here, like with this one, we could add in the argument sep is equal to the separator. It could be a tab, right, to separate multiple things, right, and then it will print out differently. But the default value, it's got a default argument just like the one I wrote, and it's by default a space. If you don't give me something, it's a space. Similarly, end by default is a new line. So we've seen that. So we've used these already without actually knowing what they are. Now we know how to write them in our own function. So now that allows us to basically say we can use this hold at 20 function to do something other than 20 if we wanted to. So now it's a bit of a misnomer now, but whatever. But now we can structure this the same way. We're going to have our outcomes is equal to a dictionary. We always know that no matter what our limit is, it's going to be from 0 to 0. We're always going to have 0 as a possible result of being a roll because we could always roll a 1 and therefore score no points in the turn. Everybody following there? Now, let's go ahead and populate our dictionary with all the other possible results. What the possible results are. Why? Because then if we do this now, we don't have to sort it later. So for score in range, and so blank. So the limit is going to be whatever it is, right? Here it was 20. Okay, and the idea here is that if my limit is if I say hold at 20, that means that I will return a score of 20 if I land directly on 20, but it's possible I score more than that, like 21 or 22 or 23 or 24 or 25, right? Those are the possible results I could have, right? I could get 20, and the way you get 25 is that if you have, if you get 19 points in a turn and then you roll 6, then you'd have 25 and then you'd stop. Okay, you can't get 26 points in a turn because to get to 26, you'd have to roll at least 20 points and then roll something else. So those are the rank. So there's 6 possible values there. Similarly, if the result was 30, it would be 31. It would be 30. If we said hold at 30, it would be 30, 31, 32, and so on and so forth. Let's choose maybe 47. Let's go ahead and choose 42 as our stopping point number. If we said our strategy was 42, then stop at 42, we'd get 42, 43, 44, 45, 46, and 47. We couldn't get 47 would occur is that if we rolled 41 points and then rolled a 6 after that. That's the highest value we could get. We couldn't get a 48 because that would require us to get at least 42 points in advance first. So the range here is limit up to limit plus 6. Up to but not including limit plus 6. And then we just simply just do outcomes. The number of times I've seen that score is initialized to 0. That's it for that. Next, we do the actual Monte Carlo approximation for in range trials, right? How many times I want to do this? I want to do this trial number of times. And what we're going to do is we are going to do hold at 20. We're going to do a simulation, but rather than doing it at 20, we're going to ask to do it for the limit. Right? Rather than doing 20, we're going to do it for the value that's been passed in. I'm going to say our score is equal to that amount. And then we go ahead and say outcomes. The number of times I've seen that score as an outcome is the number of times I've seen it plus 1, right? Increment the number of times I've seen that score plus 1 in my outcomes. Make sense so far? So now, and then finally, we just want to make sure that we'll go ahead and print our values. For score in range, not range, but score in outcomes, for each possible score in our outcomes, we're going to print the score, that score, and then we'll print the number of times that score occurred, divided by the total number of trials. We don't want to print out how many times it occurred. We do number of times it occurred divided by the total number of rolls to get percentage, right? So let's go ahead and run it. Okay. Hold at 20 outcome. Hold at X outcomes. Okay, over here, let's do, so here, let's go ahead and do 20 like we originally were doing and 100,000. That's like what we had originally. Oops, that's going to take forever. So no prints over here. And we get the same we get very similar results to what we had, which was a 10% chance of getting a 9, a 10% chance of getting a 9, a 62% chance of losing, of getting no points, but otherwise getting a 38% chance of getting points. If we decided to go with the hold at 10 strategy, we'll see that that's not necessarily too much. It's not too much better. We get a 40% chance of going bust In other words, getting no points. A 40% chance of rolling a 1, and we get a 10% chance of getting, a 16% chance of getting 10 points, a 15% chance of getting 11 points, and only 2% chance of getting 15 points. So, a lower chance, that feels not great because you had at least a 10% chance of getting 20 points if we went with hold at 20. On the other side of things, if we tell the computer, okay, your strategy is try to get at least 30 points a turn, this becomes a lot more high risk. You get a 3 in 4 chance of going bust. And a 6% chance of getting 31 points, a 6% chance of getting 30 points, and a 1% chance of getting 35. At that point, you might as well YOLO and go for broke, which I find the results to be actually extremely interesting. So what if I tell the computer for your strategy that their strategy is YOLO? Either win the game or don't win. Go for 100. Your strategy is go for 100 points, or get 0 points. So let's go ahead and see what that outcome is. It's actually pretty interesting. Your outcome is that, of course, as you'd expect, is very unlikely that you're going to win, but it is actually probably bigger than you thought it is. You've got a 99% chance of losing, which means there's a 1% chance of just winning outright in a single turn, and 1% chance is. That's more than 0. It's actually it's often enough that it would be spooky, right? Here you've got percentages that barely add up to 1%, but the computer can win. All right, Control C. And let's go, and I'm going to go ahead and even though I'll try to upload this to Discord, I'm going to go ahead and just paste this in. Okay. There you go. And to answer a question, you can do your final project in any language and in any tool. Right? You don't have to use idle. In fact, you wouldn't be able to use idle for a lot of things. That is the whole file as right now. Okay. So let's go ahead and introduce it. Let me go ahead and introduce at least, rather than doing more Monte Carlo, I think you might be more interested with the last 20 minutes taking a look at part 4. At least taking a look at and having me explain parts 4 and 5 and 6. Every part of this builds on what we're trying to do. Every part of this builds up. Okay. Okay, and it is pig. There it is. Not Pong, pig. Okay, pig. There we go. And I think I said I'd cover through at least part 4 in class, so I want to make sure and I think that today is basically my only chance then as a result. So let's go ahead and do this. So now we've got hold at 20 or goal turn. So here we were just doing a single kind of strategy, a single kind of idea of, so earlier we were just basically just going for a single turn without any kind of observation about what we might need to do later. Like, we didn't care about the score. However, we do care about the amount of points we already have. Suppose you have 90 points, right? Suppose you currently have 90 points, and your strategy is hold at 20 points, right? At that point, you want to make sure you only get 10 points or more. as opposed to getting 20 points or more. It's the difference between having a 40% chance of winning the game versus a 60% chance of winning the game. Right? Because we saw that holding at 10 would give us a 40% chance of winning. So here, what we're going to do is that we are given a player's score, simulate a single turn of pig, and then we stop when the turn total is greater than or equal to 20, or the score plus the total turn, the score plus the total you made that turn is greater than 100. In other words, either get 20 points or win the game. That's your stopping point. If you've won, you want to stop rolling. Because if you don't stop rolling, you could lose. Right? Makes sense to everybody? Now, this is a common issue with part 7 and 8. Sorry, with part 8 actually, where when you've programmed to play against the computer, and the computer stopped, get something like 115 points because it didn't stop rolling when it won. You want it to be able to stop rolling as soon as it knows it won. Right? First, give them a prompt for the score. So here, right, we give them initial score. It rolls a 2, a 3, a 4, a 4, and we get 13 total points for 403. Right? It doesn't go above 100. It stops rolling once it got to 100 or more. Okay. So here, what we're going to do is that we're going to do, and again, I'll walk us through this from that. Def, hold at 20 or goal. Limit is equal to 20. We'll go ahead and use the same kind of structure. Limit is equal to 20. And what we'll do is that, again, we have our score for the turn is equal to 0. We'll want to return that at the end. Return score. Or rather, we don't want to call it score anymore because we take in a score. So we're going to call it our turn total. The amount of points we've made that turn. Turn total. Because we take in a limit, it's equal to 20, and a score, and I'll just also give that a default value of 0. So if you don't give me anything, it's going to assume you have no points, right? But here, limit is equal to 20, turn total is equal to 0. And what we will do is we will say, now previously we had while turn total is less than the limit, right? We would do the following, which was roll it, and then if the roll was 1, we'd stop. Otherwise, add it on. So turn total roll is equal to random dot rand range 1 to 6. If roll equals 1, turn total is equal to 0. And where did I put? Yep. I'm just going to grab the print statement over here. Roll is equal to, once we roll the dime, we'll print out our roll. If the turn total is equal to that, return print turn total is equal to, no, we'll just simply say turn total is equal to that, break. We're going to actually be returning something else. So if roll is equal to 1, turn total is equal to 0, break out of this loop. Otherwise, what we're going to do is we're going to say turn total plus equals the roll. So this is what we were doing last time, essentially. Stop when we roll to 1, or add in the amount of value, stop, and then once we've rolled enough points to exceed our goal, the number of points we wanted to get, then we'll stop rolling. But now we have that second condition, which is that we want to stop also if the amount of points we've scored so far plus our current score, so the amount of stuff we got this turn plus the amount of score we already have would be is enough to win us the game. So here, turn total. So while this is true, and turn total plus score is less than 100. Remember, 100 points to win the game. Make sense? So this stop if this is no longer true, or if this is no longer true. So that becomes an and as a result, if you think about the logic for a bit. Okay? So both of those things have to be true. So that means, as a result, what we're going to return is the score. What we're going to do is that we are going to have something called a new score over here. New score is equal to the number of points we had to begin with, plus the number of points we got this turn, and then print new score, comma, is going to be new score, and return that amount. Okay, so here I'll simply give it the same values, which is hold at 20, and suppose we already have 90 points. We'll run it. You don't need to actually print it out here. And open it up, and we'll see here that we rolled a 2, a 3, a 3, a 4. So 92 points, 95 points, 98 points, 102 points. So we got 102 and we stopped. If, on the other hand, we started with 70 points, here we end up with 90 points after rolling a bunch of 3s, a 4, and 2 2s. Here we rolled a 1 to begin with, and so we ended up with no extra points. Tick. And let's go ahead and put this into the chat for you. So that is part 4. Now let's go ahead and walk through now let me go ahead and discuss the last parts before I dismiss class, okay? The last parts of this one are, so there's 4 more parts to this. I've basically done half of this for you in class. So now, what we want to do is essentially, part 5 is now simulating essentially an entire solitaire game of Pig. Basically start at 20 points and basically show one player playing through the entire game. Okay? Just playing against himself, trying to get to 100 points as soon as possible. Okay? Part 6 says, now that you've got the code, right, this obviously uses part 4's code. Part 5's code will be used to do part 6, average Pig turns, the other Monte Carlo part of this. And this says, okay, you've just done a game of solitaire with Pig, right? You've basically played a one-play version of Pig. On average, how many turns does it take to win? Not how many dice rolls. How many turns does it take to win? Your result should be around 12 to 13, right? Notice that here they did a million games and they got 12 and a half about. So that's around what you should get for the average number of turns it takes to win if you're using that strategy, the hold at 20 strategy. Part 7 and 8 are now 2-player games. Part 7 is basically making it so that you can play, making it interactive. That's the big interactive portion of it. Making sure that you and somebody else can play a game of Pig. You versus another person. So you'll have to keep track of 2 people's scores and swap between them. And part 8 is the same thing, except you're playing against, is that you program the computer to use the solitaire strategy. The computer doesn't really care about how many points you have. It will try to use its strategy regardless. Okay? And that's Pig. And once you're done with that, you'll have done the Pig assignment, which is the last of the proper homework. So I'm still trying to figure out how regular expressions will be graded, whether it'll be an extra credit assignment or if it will replace a grade. I'm inclined for extra credit. But that's it for today's lecture. All right, remember, I will send out an announcement, but the next lecture will be held over Zoom.